Hello everybody, getting ready to do lesson 11.2 part 1 classwork for pre-calculus math today. And for today's classwork lesson you got 10 points to go in your notebook guide, and then 44 points here on your classwork sheet. So have those out, and then we go into our bell work students and teachers, our bell work for today. Identify the type of conic represented by the equation. Use a graphing utility or calculator to confirm your result. So go ahead and tell me what kind of conic there is here, and then graph it. So teachers, give your students about 5 minutes. Pause your video for 5 minutes. See you in 5. Okay, welcome back everybody for today's solutions to today's bell work. Here is what your graph will look like for this expression here. You have a sideways parabola like that, and here is our equation. Our E equals 1. When your eccentricity equals 1, you have a parabola like that. So that's what we got. And then down here, this is what your equation is. So you have E equals 2 over 3. You have an ellipse, less than 1, so it is an ellipse. And this is what your equation should look like. And then this is your graph. So that's what you should have for today's bell work. On into today's lesson, dividing out technique. In Section 11.1, you study several types of functions whose limits can be evaluated by direct substitution. In this section, you will study several techniques for evaluating limits of functions for which direct substitution fails. Suppose you were asked to find the following limits. So we have a limit as x approaches negative 3 for x squared plus x minus 6 over x plus. So what would you do there? The direct substitution fails because negative 3 is a 0, in this case here, of the denominator. By using a table, however, it appears that the limit of the function as x approaches negative 3 is negative 5. So here, yeah, I mean, you have negative 5.001, and then over here, negative 4.9999. So you think, oh, negative 5 will go in there. Another way to find the limit of this function is shown in example 1. So, I mean, if you did stick in negative 3 there, it would make this function undefined. So you wouldn't have a negative 5. Okay, so going into example 1, dividing out technique, find a limit for this. And we're back to the previous limit there. Begin by factoring the numerator and dividing out any common factors. So if we factor the numerator, this numerator up here, we'll come up with these two binomials, x minus 2 and then x plus 3 over x plus 3. And then when you have that, these will cancel out. You'll have x minus 2 over 1, shouldn't we? So we have x minus 2. So as limit as x approaches negative 3 for x minus 2, we have negative 3 minus 2, and then when we do that, we come up with negative 5. So that will be our direct substitution way of doing it, rather than just by looking at that expression without unpacking it, without factoring it. Okay, use a graphing calculator to confirm your result graphically. So we have this thing here. As x approaches 2 for x squared minus x minus 2 over x minus 2. So you say, oh yeah, you know, when x equals 2, it's undefined. But by factoring it out, x minus 2, x plus 1, these will cancel. And then you have x plus 1 over 1. So now as the limit of x plus 1 as x approaches 2 will become 3. So when you take your time and factor first, you'll come out with a different solution there. Okay, this procedure for evaluating a limit is called the dividing out technique. The validity of this technique stems from the fact that when two functions agree at all but a single number c, they must have identical limit behavior at x equals c. So that's kind of like the idea behind it. In example 1, the function is given by f of x equals x squared plus x minus 6 over x plus 3, and g of x equals x minus 2. agree at all values of x other than x equals -3. Say they agree at all values of x except x equals other than x equals -3. So you can use g of x to find the limit of f of x. So you can find g of x here to find the limit of f of x. The dividing out technique should be applied only when direct substitution produces 0 in both the numerator and the denominator. An expression such as 0 over 0 has no meaning as a real number. It is called an indeterminate form because you cannot, from the form alone, determine the limit. When you try to evaluate a limit of a rational function by direct substitution and encounter this form, you can conclude that the numerator and denominator must have a common factor. After factoring and dividing out, you should try direct substitution again. So it's important to factor first when finding limits. Dividing out technique, find the limit of this now, x minus 1 over x cubed minus x squared plus x minus 1 as x approaches 1. So begin by substituting x equals 1 into the numerator and denominator. And when we do that, we have 1 minus 1 equals 0, numerator 0 when x equals 1. And then in the denominator, x equals 1 in the denominator when we substitute 1 in there. So what do we have then? So we have, because both numerator and denominator are 0 when x equals 1, direct substitution will not yield the limit. To find the limit, you should factor the numerator and denominator, divide out any common factors, and then try direct substitution again. So in this situation here, we're going to factor the denominator out. We come up with that. So now these will cancel, divide out common factors. So we have 1 over x squared plus 1. We can simplify that. And then now, direct substitution, we substitute in our 1 now. Well, 1 squared plus 1. And we get 1/2. This result here is shown graphically. So it would be right here. F is defined when x equals 1 for that situation there. 1 and 1/2. So, knowing that, we can move into this one. Find a limit if it exists. Use a graphing calculator to confirm your result graphically. So we have t cubed minus 8 over t minus 2 as t approaches 2. So with that situation here, we can factor this down. T minus 2 times t squared plus 2t plus 4 over t minus 2. These will cancel, and then you're left with t squared plus 2t plus 4. As t approaches 2, we end up with this now. 4 plus 4 plus 4 will equal 12. 4 plus 4 plus 4 equals 12 for that one. Rationalizing technique. So another way to find the limits of some functions is first to rationalize the numerator of the function. This is called the rationalizing technique. Recall that rationalizing the numerator means multiplying the numerator and denominator by the conjugate of the numerator. For instance, the conjugate of radical x plus 4 is radical x minus 4. So that would be how we would rationalize what we need to rationalize. So find the limit of radical x plus 1 minus 1 over x as x approaches 0. So it would just go x equals 0. It's not going to make any sense. So by direct substitution, you obtain an indeterminate form 0 over 0. And so that is a dead giveaway that we need to do some factoring. In this case, you can rewrite the fraction by rationalizing the numerator. And we're going to do that by multiplying by 1. And so we multiply numerator and denominator by that. And then once we multiply that out, we get x plus 1 minus 1 over this quantity down here, x times quantity radical x plus 1 plus 1. So we multiply through, we have that, and then we cancel out here, and we have x. See, this would be x plus 1 here. X over quantity x multiplied by radical x plus 1 plus 1 We can simplify this to this, because 1 minus 1 will be cancel out, and you'll just end up with an x up here. Then we can divide our common factor here. These will cancel out. Then you're left with that. So we have 1 over radical x plus 1 plus 1. We can simplify. Then once we have that, you can evaluate the limit by direct substitution now. So when we have this, now this becomes this. And then when we plug in 0 here, we have 1 over radical 0 plus 1 plus 1, which is 1 plus 1, which is 1 over 2. So that's what we're left with there. You can reinforce your conclusion that the limit is 1/2 by constructing a table as shown below, or by sketching a graph. So here's your table here, and then here is your graph here that supports the fact here that the limit is 1/2 by constructing a table. So when x equals 0, y f of x would equal 1/2 here. F is defined when x equals 0, basically. And so for here, it'd be 0.5 is what it would be. Okay, let's try one here. Find a limit if it exists using a graphing calculator to confirm your result graphically. So we have radical 5 plus y minus radical 5 over y. And we take the limit as y approaches 0. So when we do that, we end up with this here. We use a conjugate up here. We end up with this up here in our numerator over this. And then these cancel each other out. Your y's cancel. We have 1 over radical 5 plus y, radical 5 plus y plus radical 5. And then when we have that, we end up with the 1 over 2 times radical 5. And then we rationalize our denominator. And we end up with radical 5 over 10 would be the solution to as limit as y approaches 0. And that is 11.2, part 1, pre-calculus math classwork lesson. Email me at animatedpowerpointmathvideo@aol.com for questions or course materials. Thank you very much.